this is now an example of, and as I'll show you when I compute it, how you use the short-term dynamics. In this case, short-term dynamics will be our transition matrix, or it'll be a shift on world of all possible sequences to obtain infinite time result. And here all the steps will be clear. So now how do we compute the number of walks? We'll actually have an explicit formula. So if I start someplace, at state j, then I'll end up someplace in one step in time, and I'm only allowed to end up in regions for which this is 1. So I'll count 1 if I'm allowed, 0 if I'm not. Then wherever I end up, next step in time, k1, I'll end up in the region k2, and I'll go on doing this, and eventually I'll end up, after n steps in time, if I'm interested in finding transition in n steps in time between I and j, I'll end up I, and the number that I'm computing, this number here, is actually, I get a 1 every time I'm allowed to have a path, and I sum over all intermediate states, but I sum over all admissible path, because if this intermediate state is such that this is 0, it doesn't matter. So this is sum of admissible path. Walks, paths, whatever. So while my transition matrix has entry 1 or 0, the power of it will have entries which are integer, and these integers are just counting the ways of getting from I to j. For example, you have 3 disks, in how many ways I can step 2 times through 3 disk system. What I look at the square of Tij, which is the matrix that I had before, 0, 0, 0, 0, 0, 0, twice, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And you multiply it, and you see that, you get 1 in a corner, etc. So if you multiply this, you get 2, and you get 1s elsewhere. And what is this 2? If I have 3 disks, there are 2 ways in which I can go from a disk and bounce back 2 returns. But if I go from 1 to 2 to 3, there is only, 1 way to go from there, because I'm not allowed to go back. That's why I have 1s here. So entries are just the numbers of the disk. So it means that we have an explicit formula for Kn, which is sum over all initial conditions and all final conditions, because we are counting all paths, of t to the n. So if I have a transition matrix in 1 step, I have an explicit formula for transition matrix in n steps. So now, how do I use this? These are matrices. They have eigenvalues, and they have eigenvectors. So what I can write for any t, I know that it satisfies the equation phi a equals lambda alpha phi alpha for some set of eigenvalues, which is at most as large as the matrix itself, and there could be degeneracy, so it might be smaller, and eigenvectors phi, which are, this is n by n matrix. So the eigenvectors are n vectors. So now what we can do is, you can write this as a unit vector t to the n times another vector, and then you can rewrite this vector in the basis, some coefficients, alpha times the eigenfunctions. Acting on it, we just get sum over BA lambda A times the vectors phi multiplying this vector here. So there's a column, so when I multiply, I get some other number, and I'll get sum over B alpha, lambda alpha, some other number. To the nth power, of course. So if I know the eigenvalues and eigenvectors of my transition matrix, I have an explicit computable expression for the number of trajectories for any n. And in particular, I have an expression for infinite time. So in infinite time, I can look at the limit because I know that my topological entropy is limit of this thing. So I can look at h, which is limit, time goes to infinity, 1 over n of logarithm of this formula that we have, which says that k is the sum of some coefficients B alpha eigenvalues of this matrix. So logarithm of this object. And I told you before that if the matrix is such that it's strictly positive, at least after some number of iterations, meaning that I can reach every node or every partition from any starting partition, that matrix is called Perron-Frobenius matrix. So it's a matrix is positive, and strictly positive. And about it we have a very good intuition. It has a leading eigenvalue, and there's a nice theorem called, I think it's called Perron theorem, which says that the leading eigenvalue is positive and isolated. I mean, it's obviously positive because the matrix is positive. And the intuition is that what happens for the leading eigenvalue, that if you start with some space, then the transition matrix will be pushing everything into a parallelepiped which will be dominated by the leading eigenvalue. So that this thing, we'll be able to write it as logarithm of C, and the leading one, let's call it start at 0, will be 0 to the nth power. Sum plus some constants. I'm getting off the limits. So we're looking at 1 over n logarithm limit of C0 lambda to the n 0. I'll divide it in this whole series. The first term here is 0, and the second term is C1, C2. The next eigenvalue, which by definition is non-leading, so its magnitude is smaller, and we assume there is a gap. And that's what Perron theorem proves. This to the nth power. So this number is getting very small. A logarithm, we can write this as 1 over n logarithm of C0, 0, plus 1 over n logarithm of 1 plus this sum of things that are exponentially small compared to 1 as we go to the n. And in the limit, n goes to infinity, logarithm of constant divided by n will go to 0. So from here we only pick up logarithm of lambda, the leading eigenvalue of transition matrix, to the nth power divided by n, which cancels, plus 0. And we get an explicit formula for topological entropy, which says that topological entropy is simply the leading eigenvalue logarithm of transition matrix. So we know this is true in our simplest calculation here, because as we went forward in future, we get powers of 2 in every step, and the logarithm of 2 is what showed up in this bound. This is our upper bound. So entropy is the rate of increase of number of trajectories per step. And one definition of chaotic dynamics is that we have local instabilities, so that the local stretching exponent, colloquially called the Lyapunov exponent, is positive. But then we also have exponentially growing number of possible ways of going forward or recurring. In other words, we have positive entropy. So if this number is strictly larger than 0, meaning the leading eigenvalue is larger than 1, then we have exponential growth of trajectories, which is, pretty worrisome, because we'll be herding cats and there'll be exponentially growing number of cats. This is incredibly good news, because this is a characterization of infinite time behavior of a chaotic system. And this is something that's computed in one time step. So if I just know the transition matrix, that means what happens in one time step, I will always know its eigenvalues. And I only need the leading eigenvalue, and that'll give me the infinite time behavior. And this is the essence of everything you do from now on. Even though it's impossible to count all trajectory, they're all exponential and stable, they're Lyapunov times, if you ask yourself what happens at infinite time, you'll be able to make a prediction from finite time.